You've found Dreamtime Science, a peaceful corner where we unravel the mysteries of our universe one whisper at a time. Let the gentle current of discovery carry you towards sleep. You know what's fascinating? These tiny bits of the Earth called rare Earth elements. They're not actually all that rare, but they're absolutely essential to so many parts of our modern world, from the screens we stare at to the cars we drive. I've been thinking about how something so small and hidden beneath our feet quietly powers so much of our everyday life, and I can't wait to share why these elements are quietly shaping the future in ways we might never have imagined. If you find peace in these nocturnal discoveries, consider becoming a regular visitor to our quiet corner of science. Share in the comments what topic you'd love to dream about next. Take this moment to settle in, wrap yourself in comfort, release the day's weight from your shoulders, and let your breath become as gentle as starlight. In the hush of the evening, as the world softens into gentle gradients of dusk and the city's bright eyes begin to flicker on, you might take a moment to wonder about the hidden engines beneath our familiar realities. All around us, invisible and unheralded, there are materials that quietly enable the magic of modern life, a secret alphabet of elements, tucked deep within the bones of our devices, vehicles, and cities. Tonight let us drift into the story of these enigmatic actors, the rare Earth elements. Their names rarely grace the headlines, yet they are the silent architects of the digital age, the invisible backbone of technology. Take a breath and look around your room. Perhaps your phone is charging softly by your bedside, its glassy face aglow with messages from distant friends. Maybe, nearby, a laptop slumbers, waiting to be woken with a tap. In the corner, a small, powerful speaker might be humming a lullaby, coaxing you toward sleep. All these objects are utterly mundane, yet deeply miraculous, the fruit of centuries of scientific discovery and engineering ambition. Each, in its own way, is a cathedral built from the tiniest building blocks nature can muster. But what is it truly that makes these devices so much more potent than their ancestors? What is the secret sauce that flavors modern technology with such power and subtlety? If you have ever seen the inside of an old first-generation mobile phone, you'd have glimpsed a tangle of wires, slabs of silicon, and the occasional copper coil. But the phones of today, impossibly slim and astonishingly powerful, are the result of an alchemy that draws on elements you might never have heard of. Elements with names that sound like they belong in a wizard's grimoire: neodymium, lanthanum, praseodymium, dysprosium, terbium, and more. These are the rare Earth elements. Despite their name, rare earths are not especially rare in the crust of our planet. They are scattered widely, hiding in the soils beneath our feet, dissolved in riverbeds, sleeping in the hearts of mountains. Yet they rarely appear in concentrations dense enough to be easily harvested. Their true rarity lies in their accessibility, in the difficulty of coaxing them out from the embrace of ordinary rocks. This, perhaps, is why they have managed to remain so anonymous, so quietly essential. They are the backstage crew, the ones who pull the curtains and shine the lights, all while remaining unseen. When you press a button, swipe a screen, or ask your digital assistant for the weather, you are in dialogue with rare earths. The vibrant hues that dance across your display are painted by phosphors containing europium and terbium. The tiny, fierce magnets that let your headphones sing are forged with neodymium and dysprosium. Even the gentle vibration that alerts you to a new message is made possible by rare earth alloys, allowing for minuscule yet powerful motors. Without these elements, our world would be duller, heavier, slower, a shadow of its current self. To see their story more vividly, let us slip sideways into the world of science fiction and pop culture, where imagination often races ahead of reality and the possibilities of matter are stretched to their limits. In these tales, rare and mysterious elements are the keystones of futuristic societies. They power starships, grant superhuman abilities, and sometimes threaten the very fabric of existence. The unobtainium of Avatar, the vibranium of Black Panther, the dilithium crystals of Star Trek, these are all fictional echoes of a real-world desire to find, in the periodic table's hidden corners, materials that unlock new realms of possibility. There is a poetry in the way science fiction writers have intuited the importance of rare elements long before the world at large recognized their significance. The notion that a single, hard-to-find material could shift the balance of power or fuel an entire civilization is not so far from the truth. In our own time, rare earth elements have become the currency of progress, quietly underpinning the rise of renewable energy, advanced electronics, and military technology. They are the magic matter that bridges the tangible and the imagined. But let us return from the stars to the solid ground of Earth, to the true origins and properties of these elements. The rare earths are not a single family, but a gathering of 17 elements, the 15 lanthanides, along with scandium and yttrium, which often occur alongside them. Each possesses subtle quirks of chemistry, lending them to specialized uses. Lanthanum, for instance, is a key ingredient in camera lenses, helping to bend light with greater precision and clarity. Cerium is found in catalytic converters, scrubbing toxins from car exhausts. Gadolinium, with its powerful response to magnetic fields, is used in MRI machines, rendering the invisible inner landscapes of our bodies in exquisite detail. It is in the domain of magnets, however, that rare earths perform some of their most vital and astonishing tricks. Neodymium, when alloyed with iron and boron, becomes the beating heart of the strongest permanent magnets known to science. These tiny powerhouses are what make modern headphones feather-light and efficient, enable wind turbines to spin with minimal resistance, and allow electric vehicles to glide silently along our roads. Imagine the grace of a maglev train, floating frictionless above its rails, or the compact might of a drone's electric motor, all made possible by the quiet presence of rare earths. Yet for all their utility, rare earth elements are not just tools, they are windows into the deep structure of matter itself. Each tells a story that stretches back to the birth of the universe, to the cataclysmic deaths of ancient stars. In the supernova's violent heart, nuclei fused and fractured, forging the heavier elements in a cosmic crucible. Over billions of years, these fragments drifted through the void, seeding planets like our own with the raw materials of future worlds. That the rare earths are buried in the crust of our planet is a kind of cosmic accident, a testament to the long, improbable journey from stardust to smartphone. Their journey into human hands has been no less dramatic. The first rare earth element to be discovered was yttrium, unearthed in the late 18th century from a quarry in the tiny Swedish village of Ytterby. Over the next 100 years, chemists teased apart the identities of the lanthanides, often naming them in homage to their origins: ytterbium, terbium, erbium. Each discovery was a triumph of persistence and ingenuity, for the differences between these elements are subtle, their chemical personalities nearly indistinguishable. For a long time, rare earths languished in obscurity, their uses limited and their supply abundant. It was only with the onset of the electronics revolution in the late 20th century that their true value began to emerge. Suddenly, their peculiar properties were in demand: their ability to emit colored light, their magnetic strength, their affinity for electrical currents. As devices shrank and became more sophisticated, the rare earths stepped onto center stage, though still shrouded in anonymity. In the world of pop culture, this anonymity makes them ripe for reinvention. Writers and filmmakers, searching for metaphors of power and scarcity, often invent new elements whose names echo the cadence of the rare earths: unobtainium, a substance so rare as to be almost mythical; adamantium, the indestructible metal that clads Wolverine's bones; vibranium, a source of endless energy and resilience; These fictional materials serve as symbols for humanity's restless quest to harness the hidden forces of nature, to bend the fabric of reality to our will. Yet even as fiction spins its wildest dreams, the real rare earths quietly shape the world in ways more profound than any fantasy. Consider the touchscreen on your device, which responds with uncanny sensitivity to the brush of a fingertip. Within, layers of indium tin oxide conduct electricity with near-invisible finesse, guided by the subtle influence of rare earth dopants. Or think of the LED bulbs that illuminate your home, sipping at electricity while bathing your rooms in warm natural light. Their glow is made possible by phosphors laced with europium and terbium, orchestrating a symphony of photons that mimic the sun. In the vast data centers that pulse beneath the surface of our digital world, rare earths are present too. Hard drives spin on axles driven by neodymium magnets, storing the collective memory of humanity with speed and reliability. Fiber optic cables, sheathed in glass, doped with erbium, carry our voices and thoughts across continents in beams of light. Even in the quiet fields where wind turbines turn and solar panels glimmer, rare earths are at work, transforming the sun's energy and the wind's breath into currents of power that sustain our way of life. All of this, and yet, if you were to hold a pinch of rare earth ore in your hand, you might not recognize its worth. The elements themselves are often drab and unassuming, chalky powders, greyish metals, unremarkable in appearance. Their value lies hidden in their atomic structure, in the arrangement of their electrons, and the subtleties of their chemistry. It is here, at the smallest scales, that their magic emerges, the ability to emit coloured light, to channel magnetic fields, to catalyse reactions with uncanny efficiency. The story of rare earths is not just a tale of technology, but a meditation on the hidden architectures of the world. So much of what we rely on is built atop invisible scaffolding, delicate networks of matter and energy whose workings are known to only a few. There is something humbling about this, a reminder that the most essential things are often those we never see, never pause to consider. From the glow of a screen to the whisper of a wireless signal, rare earths are the secret agents of modernity, shaping our lives in ways both intimate and profound. And yet, as twilight deepens and the city outside your window slips into the hush of night, questions linger. Where do these elements come from? How are they coaxed from the earth, refined and woven into the fabric of our devices? What are the consequences, scientific, environmental, even geopolitical, of our reliance on these hidden treasures? In the darkness, the story of rare earths stretches onward, a thread running through the loom of our technological dreams, waiting to be followed into deeper mysteries. In the gentle hush of night, imagine yourself descending into the earth not as a miner, but as a silent observer, a drifting mind, weaving between seams of ancient rock. Here, far below the surface, the world is not shaped by sunlight, but by pressure and time. The rock is dense, veined with secrets, and within its heart lie the rare earth elements, those elusive actors upon which the machinery of modern life depends. Tonight, let us drift through this unseen tapestry, unweaving its threads, pondering the strange nature and stubbornness of these elements that have, for so long, eluded the easy grasp of humankind. Rare earth elements, 15 siblings in the lanthanide family, trailed by scandium and yttrium, are not, as their name might suggest, truly rare in the universe. In fact, some are more plentiful than precious metals. Cerium, for instance, is more abundant in the crust than copper. Yet abundance in the secretive world beneath our feet is a matter of context. Like a handful of salt in a vast ocean, rare earths are scattered in such a way that their presence is diffuse, their extraction a challenge of infinite patience and ingenuity. The lanthanides, lanthanum, cerium, praseodymium, neodymium, and their kin, are a row of elements with atomic numbers 57 through 71, nestled quietly between barium and hafnium on the periodic table. If you were to peer into their atomic hearts, you would find a slow, steady increase in complexity as you move from one to the next. Each new member adds a single proton to its nucleus and an electron to a hidden shielded shell, the 4F subshell, a haunted corridor where electrons whisper and jostle, rarely peeking out to the outer world. This is the defining trait of the rare Earths. Their electrons, buried deep within, grant them properties both subtle and profound. Consider their colors, which are not those of simple pigments, but of quantum transitions. When rare earth ions are dissolved in crystals or glasses, they impart ethereal hues. Europium gives a soft red glow, terbium a gentle green, neodymium a pale violet. These colors arise from the unique arrangement of their 4F electrons and the curious fact that, unlike the outer electrons of other elements, the 4F electrons are partially shielded from their environment. This shielding means their energy levels are exquisitely sensitive, yet oddly consistent, leading to sharp, almost laser-like emission lines, perfect for the world of phosphors, lasers, and color displays. But it is not only color that makes the rare earths extraordinary. Their magnetic properties, too, are a study in paradox. Gadolinium, for example, is ferromagnetic at room temperature, joining the ranks of iron, cobalt, and nickel. Yet when alloyed with other rare earths or partnered with transition metals, the results can be astonishing. Magnets of unprecedented strength, the very heart of wind turbines, headphones, and the spinning disks of computer hard drives. Neodymium iron-boron magnets are famed for their power and compactness, their might hidden in children's toys and Mars rovers alike. Such is the magic of the rare Earth's electron dance, each element a note in a magnetic symphony, the whole greater than its parts. It is here, though, that their abundance in the Earth's crust collides with the stubbornness of their chemistry. The rare Earths do not favor solitude. They are sociable atoms, inclined to cluster together, slipping into minerals that bear several of their kind. Cerium, lanthanum, neodymium, and praseodymium often huddle in bastnasite, a carbonate fluoride mineral. Others, like samarium and gadolinium, prefer monazite, a phosphate. These minerals are scattered thinly across the globe, and rarely do they form veins rich enough to tempt a miner's eye. Instead, they are bound tightly in a lattice of oxygen, phosphorus, or fluorine, the rare earth's true rareness lying not in scarcity, but in their reluctance to be set free. To separate the rare earths from their mineral prisons is a task that requires both patience and a subtle hand. The process begins, as all mineral extractions must, with mining, an endeavor of force and disruption. Ores are crushed and ground to a fine powder, their mineral grains exposed to the reagents that will coax out the metals within. Yet here the rare earths differ from their metallic cousins. They are chemically so similar to one another that no simple trick of acid or base will do. Instead, the ores are dissolved in strong acids, sulfuric or hydrochloric, yielding a briny soup in which all the rare earths swim together, indistinct and resolute. And so begins the great unweaving, the painstaking separation of this family of elements, each so alike in size and charge that their chemistry blurs at the edges. The methods devised to tease them apart are testaments to human patience and creativity. Solvent extraction, for instance, relies on the slight differences in how each rare earth ion prefers one solvent over another. Imagine 1,000,000 marathon runners, nearly identical in stride, being sorted by the tiniest variations in their pace. With each pass through the maze of organic and aqueous phases, the rare earths inch closer to individual purity. For every kilogram of pure neodymium or dysprosium, hundreds of steps may be required, each a drop of difference, amplified by repetition. Yet the toll is not merely in time and effort, but in waste and consequence. The acids and organic solvents used are often toxic, and the process generates radioactive byproducts, particularly when monazite is involved, for it harbors thorium, a silent companion to the rare earths. The mining sites, scarred by extraction, sometimes bear witness to environmental heedlessness. Tailings, ponds laced with heavy metals, landscapes altered beyond easy repair. The price of these elements is not only in dollars or yuan, but in scarred earth and altered rivers, in communities living in the long shadow of chemical legacy. Still, the need for rare earths persists, for their properties are not easily substituted. Their stubborn chemistry is matched by an almost stubborn indispensability. In the modern world, a smartphone is a symphony of rare earths, yttrium and europium in the vivid red of its display, neodymium in its tiny speaker magnets, lanthanum in the camera lens, cerium as a glass polisher. In each wind turbine blade, the whispering power of neodymium and dysprosium spins electricity from the wind. In hybrid car batteries, lanthanum and cerium shuttle ions back and forth, storing and releasing energy with quiet persistence. Why, then, are the rare earths so difficult to mine and process, if not for their actual rarity? The answer lies deep in the quantum fabric of their atoms, in the way their 4f electrons are shielded from the outside world. Chemically, the rare earths are characterized by the +3 oxidation state, the loss of 3 electrons, leaving behind a triply charged ion. This uniformity makes them behave almost as twins, their chemical personalities nearly indistinguishable. Cerium alone sometimes strays, adopting a +4 state, which allows for certain separations, but for the most part the rare earths move in lockstep, a challenge for the chemist tasked with dividing them. In the early days, separation was a matter of relentless repetition. Fractional crystallization, dissolving and recrystallizing salts over and over, each time removing a minute fraction more of one element than another, was the method of choice. It could take thousands of steps to isolate a single gram of pure element. Only with the advent of ion exchange chromatography and solvent extraction did the process become even remotely practical on a large scale. Even today, the refinement of rare earths is a slow dance, balancing efficiency, selectivity, and environmental safety. There is, too, the matter of geopolitics, a tapestry of its own. The distribution of rare earth ores is uneven, and the expertise and infrastructure to process them rarer still. China, with vast reserves and an early investment in refining technologies, has long dominated the global supply. Other nations, wary of dependence, seek to open new mines, to develop cleaner and more efficient extraction methods, to recycle rare earths from old electronics and magnets. Each advance is a thread in the larger story. The world's growing understanding that these elements, so essential to the clean energy transition, to defense, to communication, must be stewarded with care. The rare earth tapestry is thus woven not only from atoms and bonds, but from human stories, of ingenuity and oversight, of invention and consequence. Each element has its quirks. Europium's gentle red glow, used to make television screens vivid in the dark, samarium's quiet strength, alloyed in powerful permanent magnets, lutetium, the rarest of the rare, finding its niche in medical imaging and cancer therapy. Their names, echoing ancient places, Itaby, Syria, Turbia, are reminders of the long journey from mysterious mineral to modern marvel. Yet, as we contemplate this tapestry, it remains unfinished, its threads crossing and recrossing, new patterns emerging as technology evolves and our demands shift. The search for cleaner extraction methods continues, inspired by the quiet resilience of bacteria that can bind rare earths, or by the promise of ionic liquids that might separate the elements with less environmental harm. Researchers study the deep ocean floor, where nodules rich in rare earths lie undisturbed, awaiting technologies that might one day harvest them without wrecking fragile ecosystems. Others peer into the recycling bins of the world's cities, searching for ways to reclaim rare earths from discarded electronics, closing the loop and weaving new life from old. In the quiet of night, the rare earth tapestry stretches on, a testament to the hidden depths of our planet and the intricacies of atomic structure. Each element, with its subtle properties and stubborn chemistry, is both a challenge and an invitation, a reminder that the most precious things are often those that refuse to be easily claimed. As we float through this subterranean realm, we glimpse not only the story of matter, but the story of ourselves, our yearning for understanding, our ingenuity in the face of difficulty, our capacity for both creation and carelessness. The journey through the rare earths is still unfolding, each discovery a new thread in the fabric. Somewhere in the darkness, a pulse of magnetism, a glow of colour, a whisper of electrons, each a sign that the tapestry is alive, its mysteries waiting to be unravelled further. And as we drift onward, the tapestry beckons us to follow deeper still toward the next chapter in the elemental story. Beneath the forested hills of Scandinavia, the ground is soft with moss, and the stones are laced with stories. For centuries, these ancient rocks have held secrets undisturbed, their treasures hiding in plain sight, disguised, elusive, nearly invisible to the naked eye. In the mid-18th century, as the Age of Enlightenment unfurled across Europe, curiosity and reason became guiding stars. It was in this climate that the search for the rare earth elements began, not with a flash of revelation, but with the patient, deliberate work of those who saw the world as a great puzzle waiting to be solved one piece at a time. To study the rare earths is to embark upon a journey of unmasking. The very term rare earth is a misnomer, for these elements are not particularly rare in the earth's crust. What is rare is their willingness to reveal themselves. Like shy woodland creatures, they tend to travel together, concealed in minerals where their chemical properties are so alike that separating one from another poses an extraordinary challenge. Early mineralogists and chemists, armed with little more than glassware, curiosity, and the glimmers of new scientific methods, began to unravel the riddle. The story opens in a small Swedish village called Ytterby, perched on the edge of the Baltic Sea. Here in 1787, a lieutenant and amateur geologist named Carl Axel Arrhenius stumbled across a heavy black rock in an abandoned feldspar mine. The rock, later named gadolinite, would become the birthplace of a family of elements that would forever alter the periodic table. For decades, chemists chipped away at the mystery of this stone, dissolving, precipitating, heating, and crystallizing, using painstaking methods to tease apart the constituents. In the laboratories of the 19th century, the tools were often simple: crucibles, retorts, glass flasks, balances delicate enough to weigh dust motes. Chemists would dissolve a mineral in acid, coaxing its hidden components into solution, then add reagents to draw out new compounds. They watched for subtle changes: a faint colour in the flame, a precipitate forming in a clear liquid, a shift in the weight of a residue. Each sign was a clue pointing toward an unknown substance. The very first rare earth element to be isolated was yttrium, named for Ytterby itself, its discovery marking the opening act of a long and intricate performance. As the 19th century unfolded, the cast of characters grew: cerium, lanthanum, terbium, erbium, all bearing names that evoke the places and people who first glimpsed their existence. The process was not smooth or straightforward. Because the rare earths so closely resemble one another in their chemical behavior, early scientists often believed they had found a new element, only to later discover it was a mixture. The story of terbium and erbium, for instance, is tangled with error and revision, one scientist's erbium becoming another's terbium, as methods improved and understanding deepened. The rare earths seem to mock the boundaries that science tried to draw around them, whispering that nature's categories are not always so clear. To unlock these secrets, chemists developed ever more artful techniques. One of the most elegant was fractional crystallization, a kind of chemical dance that exploited the minute differences in solubility between rare earth salts. A solution would be carefully prepared, and as it cooled, crystals would begin to form. The earliest crystals to appear would be just slightly richer in one element than in another. Chemists would collect these, dissolve them again, and repeat the process hundreds or even thousands of times. Each cycle brought the elements closer to isolation, an act of patience bordering on obsession. Another method, fractional precipitation, relied on subtle differences in how the elements reacted with particular chemicals. By adding a reagent drop by drop, chemists could encourage one rare earth to settle out of solution while its companions remained behind. The process was laborious and slow, often requiring months or years to yield even a few grams of a pure element. But the reward was profound. Each new isolation expanded the boundaries of the periodic table, filling gaps and challenging the notion that the natural world was already fully known. As science advanced, so too did the tools. In the early 20th century, the advent of spectroscopy offered a new way to peer into the elemental heart of matter. By passing light through a sample and splitting it into its component colors, scientists could detect the unique spectral fingerprints of each element. The rare earths, with their complex electron configurations, produced especially intricate patterns, each line a signpost pointing to a hidden identity. Spectroscopy turned the chemist's eye into a kind of prism, revealing what lay invisible within the minerals. The work of unearthing the rare earths was not confined to laboratories alone. Prospectors and geologists fanned out across the globe, searching for rocks that might contain these elusive elements. In the red soils of India, the monazite sands proved to be particularly rich. In the mountain ranges of China, vast deposits of bastnasite and other minerals awaited discovery. The rare earths revealed themselves in many guises, as pale yellow powders, as brittle metallic shards, as streaks of color within unassuming stones. To extract these elements from their mineral homes is a feat of ingenuity, one that draws upon the full range of human creativity. The first step is often physical, mining the ore, crushing it into fine powder, and separating the valuable minerals from the surrounding rock. This is followed by a series of chemical transformations, each carefully designed to exploit the subtle differences in reactivity, solubility, or ionic size among the rare earths. For example, in the processing of monazite, a phosphate mineral rich in rare earths, the ore is often treated with hot concentrated sulfuric acid. This reaction breaks apart the mineral lattice, freeing the rare earth elements as soluble sulfates. The resulting solution is then subjected to a sequence of precipitation and separation steps, sometimes involving organic solvents that selectively extract certain elements over others. The process can be likened to unwinding a tangled skein of threads, each element teased out by its own unique set of chemical preferences. In more modern times, the development of ion exchange and solvent extraction techniques has revolutionized the art of separation. Ion exchange resins, for example, are porous beads that can selectively bind specific rare earth ions from solution, allowing them to be washed away and recovered in nearly pure form. Solvent extraction, on the other hand, uses organic liquids that preferentially dissolve one rare earth over its neighbors, creating a cascade of separations that can isolate even the most stubbornly similar elements. These methods are both subtle and robust, requiring a deep understanding of chemistry and an intuitive sense for the behavior of atoms under different conditions. The extraction of rare earths is not merely an industrial pursuit. It is a choreography of precision and care, a testament to the interplay between human knowledge and the natural world. Each step, from the first blow of the miner's pick to the last analysis in the laboratory, is guided by the same impulse that drove the earliest investigators, a desire to see what lies beneath, to transform the unknown into the known. As the rare earths emerged, one by one, into the light of understanding, they brought with them new questions and possibilities. Their unique electronic structures, characterized by partially filled F orbitals, endow them with remarkable properties. Some, like neodymium and samarium, can be fashioned into magnets of extraordinary strength. Others, like europium and terbium, glow with brilliant colors under ultraviolet light, illuminating television screens and computer monitors. Still others, like gadolinium, possess powerful magnetic moments that allow them to serve as contrast agents in medical imaging. The rare earths are thus not only prizes to be extracted, but also keys to new realms of technology and discovery. Their study requires a blend of disciplines: the geologist's sense for the land, the chemist's mastery of reactions, the physicist's insight into atomic structure. The tools have grown more sophisticated: mass spectrometers, electron microscopes, synchrotron light sources, but the essential spirit remains unchanged. It is the spirit of inquiry, of patience, of delight in the hidden patterns that nature weaves. There is, too, a kind of humility in the study of the rare earths. Each advance has been hard-won, each element coaxed from obscurity by years of careful work. The history is littered with blind alleys, false leads, and discoveries that had to be made and remade. It is a reminder that science is not a straight road, but a winding path through uncharted territory. The rare earths, with their subtle differences and elusive natures, have taught generations of scientists to look closely, to question assumptions, and to embrace uncertainty. As we look back on the centuries-long quest to understand and extract the rare earths, we see a tapestry woven from many threads: the patience of the crystallographer, the resourcefulness of the miner, the insight of the spectroscopist, the inventiveness of the engineer. Each has played a role in bringing these elements from the hidden depths of the earth into the heart of modern technology. Yet for all that has been revealed, much remains unknown. The rare earths continue to challenge our ingenuity, both in the laboratory and in the wider world. Their extraction poses environmental and ethical questions: how to balance the demand for these vital elements with the need to protect the landscapes from which they come, how to ensure that the benefits of their discovery are shared equitably among all who depend on them. The answers are not simply, and the search for better, more sustainable methods of extraction is ongoing, a new chapter in the unfolding story. In the quiet hum of a laboratory, under the steady light of a microscope, a scientist examines a grain of ore. It is unremarkable to the untrained eye, a speck of dust among millions. Yet within it lies the potential for transformation: the glow of a smartphone screen, the precision of a satellite, the clarity of a medical scan. The tools may have changed over the centuries, but the act of discovery remains as artful as ever, a dance between human curiosity and the deep, silent patience of the earth. Beyond the laboratory, far from the mines and refineries, the rare earths continue their journey. In the next stage, their unique properties will be harnessed, woven into the fabric of modern life in ways both visible and unseen. The story of their unearthing is but a prelude to the marvels they enable, a testament to the enduring interplay between the known and the mysterious. The rare earths, once hidden in the shadows of stone, are now poised to illuminate the world in ways that even their earliest discoverers could scarcely have imagined. And so, as the scientist folds away their notes and the last echoes of the day fade from the laboratory, the rare earths wait in gentle anticipation, ready to reveal the next part of their story to those who seek to understand their quiet power. The artful science of unearthing the rare leads us forward, ever deeper into the heart of matter, ever closer to the luminous possibilities that the elements hold in their silent embrace. There are moments in the long history of humankind when a substance, silent and unremarkable to the untrained eye, quietly alters the arc of civilization. Rare earth elements, those elusive tenets of the periodic table that shimmer in the shadows between the familiar and the obscure, have, in their own way, written entire chapters of the human story. As we move deeper into the quiet hours of the night, let us linger in the gentle glow of these elements, reflecting not only on their chemistry and utility, but on the subtle, intricate ways they bind themselves to our ambitions, our imaginations, and our responsibilities. The tale of rare earths is not merely that of atoms and minerals, of spectral lines and electron shells. It is also a profoundly human chronicle, a tale of curiosity, ingenuity, and often unintended consequence. The journey of these elements, from the heart of dying stars to the palms of our hands, is entwined with our own journey as seekers and makers. When we hold a glowing smartphone, a wind turbine blade slicing air on a distant plain, or a flickering phosphorescent screen, we are holding the end point of a story that began billions of years ago and that now unspools in our age with both promise and peril. Consider for a moment the paradox of rarity. The rare earth elements are in truth not always so rare. Cerium, lanthanum, neodymium, these are not the scarcest substances on our planet, not by abundance in the Earth's crust. Their rarity instead lies in their stubborn tendency to hide, to blend with one another in ores, to resist the easy separations that make mining profitable and simple. Their rarity is logistical, not merely geological. This subtlety has shaped the ways in which human societies have discovered, extracted, and come to depend upon them. Step back into the dim-lit laboratories of the 18th and 19th centuries, where chemists hunched over their glassware, eyes straining to distinguish one pale precipitate from another. Here, in the flicker of candlelight, the very names of the rare earths, yttrium, terbium, erbium, ytterbium, emerged from a single Swedish village, Ytterby, whose quarry yielded minerals so perplexing that decades would pass before their secrets were fully teased apart. Each new element, isolated with painstaking care, was a testament not only to scientific persistence, but to a certain humility. The universe, it seemed, was willing to reveal its wonders only to those prepared to seek them with patience and respect. But as centuries turned and curiosity gave way to industry, rare earths slipped quietly into the machinery of modern life. The world's hunger for color televisions, powerful magnets, and efficient lighting drew these elements from their hiding places into the global spotlight. The arc of their journey bent from the laboratory crucible to the mine, from the mine to the factory, from the factory to the homes and pockets of billions. In this transition, the rare earths became a mirror for our own desires and dilemmas. We marveled at their power, how a pinch of europium could make a screen blaze red, how neodymium could forge magnets that lift immense weights, how lanthanum could polish glass to perfect clarity. Yet each marvel is shadowed by a cost, measured not only in kilowatt-hours or dollars, but in the scars left upon landscapes and communities. Vast stretches of land in Inner Mongolia, in southern China, in the steppes of Kazakhstan and the outback of Australia have been transformed by the pursuit of these elements. Open pits, tailings ponds and streams laced with acids and heavy metals mark the places where rare earths are wrenched from the earth. For every kilogram of refined product, there is a trail of waste, a silent record of our appetite for the invisible ingredients of the modern world. Here, the story of rare earths turns from chemistry to ethics, from mineralogy to stewardship. For in our rush to harness the subtle powers of these elements, we are confronted with questions that echo far beyond the laboratory. Who bears the burden of extraction? Who reaps the benefits? How do we balance the needs of the present with the rights of the future, the promise of technology with the dignity of people and places? At the heart of these questions lies the fundamental interconnectedness of all things. The smartphone in your hand is not merely a marvel of circuitry and software. It is also a web of relationships, between miner and engineer, between distant mountain and urban street, between raw material and refined ambition. Rare earths, by their very nature, are global citizens. They cross borders, link economies, and entwine the fate of distant lands with our daily lives. Yet, as with all connections, this web is fragile. The concentration of rare earth production in a handful of countries, especially China, has brought both opportunity and risk. Geopolitical tensions, trade disputes, and supply chain disruptions reveal the delicate balance upon which our technological civilization rests. A shortage of dysprosium or neodymium, elements essential for high-performance magnets, can ripple outward, affecting not just manufacturers, but the very fabric of modern society: transportation, energy, medicine, defense. In this light, rare earths become both a blessing and a warning. Their presence in our devices is a silent reminder that the conveniences and wonders of daily life are undergirded by a complex, often invisible infrastructure, one that demands foresight, cooperation, and care. The story of rare earths thus asks us to reflect on what it means to be responsible stewards of the materials that shape our world. Responsibility, in this context, is not merely a matter of regulation or policy, though these are essential. It is also a matter of imagination, the ability to see past the immediate, to envision the longer arc of consequence and possibility. It is the willingness to ask difficult questions about recycling and reuse, about alternative materials, about the rights of workers and the health of ecosystems. It is above all the capacity to recognize that our choices reverberate outward, touching lives and landscapes far beyond our immediate sight. Consider for a moment the ongoing efforts to develop more sustainable rare earth supply chains. Engineers and scientists are searching for ways to extract these elements with less harm, experimenting with new solvents, greener processes, and more efficient recovery techniques. Policymakers are exploring strategies to diversify supply, to reduce dependence on single sources, to encourage recycling of rare earths from used electronics and industrial waste. Each of these efforts is a thread in a larger tapestry, a collective attempt to honor the gifts of the earth without heedlessly exhausting them. There is poetry, too, in the search for substitutes. Materials scientists labor to design new alloys and composites that can perform the feats of rare earths with more abundant ingredients. The challenge is formidable. The unique properties of rare earth elements arise from the intricate architecture of their electron shells, a dance not easily replicated by other atoms. Yet this quest, however difficult, reflects a deeper truth, that human ingenuity, when guided by wisdom and care, can find ways to adapt, to lessen the burdens we place upon the planet. These scientific and technological solutions, however, are but one part of the human response. There is another, quieter dimension, a change in perspective, a shift in the way we see ourselves in relation to the materials that surround us, to hold a luminous screen or a humming motor and recognize, if only for a moment, the journey of the rare earths within. This is to remember that we are not merely consumers, but participants in a vast, ongoing exchange between the human and the more than human world. This recognition carries with it a kind of reverence. The rare earths, after all, are not mere commodities. They are the enduring remnants of cosmic violence, fragments of supernovae and merging neutron stars. Their presence in the crust of the earth is the residue of processes that unfolded before the earth itself was born, To extract, refine, and employ them is to touch something ancient, to draw upon energies and histories that vastly exceed our own brief span. Such reverence need not be mystical or sentimental. It is rather a call to humility, a recognition that every technological advance, every shimmering innovation is rooted in the patient work of nature over eons. This humility, in turn, can inform our decisions. It can remind us to value not only efficiency and profit, but also justice and sustainability, to weigh not only the benefits of rare earths, but also the costs, both seen and unseen. In the quiet hours of reflection, we might also consider the deeper symbolism of these elements. Their very invisibility, the fact that most of us have never seen a lump of gadolinium or a crystal of praseodymium, mirrors the hidden interdependencies of the modern world. We are surrounded by materials and systems we scarcely notice, yet upon which we utterly depend. To learn the story of rare earths is to glimpse, however fleetingly, the intricate webs that sustain our lives. And yet there is a certain beauty in this hiddenness. The rare earths, by their nature, invite us to look more closely, to peer beneath the surface of things. They teach us that value is often concealed, that the most transformative forces can be quiet and subtle. In a world that often prizes the visible, the spectacular, the rare earths remind us of the power of the unseen. Perhaps, too, they offer a lesson about balance. The history of rare earths is marked by cycles of scarcity and abundance, of discovery and depletion, of innovation and consequence. To be human is to inhabit these cycles, to learn from them, to seek equilibrium between what we take and what we give back. As the night deepens and the world quiets, let us hold these reflections gently. The rare earths, scattered through our technologies and our dreams, are a testament to both the ingenuity and the frailty of our species. They are a link between the remote past and the unfolding future, between the cosmic and the everyday. They call us to curiosity, to care, and to a deeper understanding of our place in the world. What will become of these elements and of us as the centuries turn? The answer, as always, is unwritten, a story still to be shaped by the decisions we make, the values we hold, the sense of wonder we preserve. The rare earths, in all their mystery and meaning, invite us to listen, to learn, and to imagine what might yet be possible. Their tale, like our own, continues, winding onward into the unknown. As our journey through the shimmering cosmos of modern rare earths drifts to a close, may the quiet glow of their hidden wonders gently settle like a comet tail fading into the hush of space. Rest peacefully now, and when your curiosity stirs again, return to Dreamtime Science, where more mysteries await to cradle you in their soft, starry embrace.